Smallness is easy to imagine at first. A grain of sand, a speck of dust, the edge of a needle. Each step down still feels connected to experience, something that could, at least in principle, be seen, touched, or measured with better tools. But physics does not stop shrinking when intuition does. Below the scale of atoms and even below the structure of their interiors, distance becomes less like something you can picture and more like something you have to define carefully. At these extremes, asking how small something is begins to blur into a different question altogether. How small a distance can even be said to exist? Welcome to the Sleepy Scientist. If you enjoy drifting through questions like this, you're very welcome to subscribe and join these quiet explorations. And if you feel like it, share where in the world you're listening from tonight. It is always grounding to know how far these thoughts travel, even while we explore the smallest scales imaginable. There is a particular length that appears when physicists take this question seriously, not as a particle, not as a physical object, but as a limit written into the structure of nature itself, a distance so small that below it, the usual idea of measurement begins to fail. This length is known as the Planck length, and its value is 1.6 times 10 to the minus 35 meters. That number does not describe the smallest thing in the universe. It describes the smallest distance that physics can meaningfully talk about. A boundary beyond which space can no longer be cleanly divided using the rules we rely on everywhere else. No microscope can reach it. No experiment can directly probe it. And not because our technology is lacking, but because measurement itself begins to interfere with what is being measured. The Planck length emerges when gravity, quantum behaviour, and the structure of spacetime are all taken seriously at the same time. It is not chosen for convenience, and it is not speculative. It appears whether physicists want it to or not, quietly signalling that there is a scale where familiar descriptions of distance stop applying. This video is about that length, what it is, why it exists, and what it means when the universe places a limit not on how far we can measure outward, but on how precisely we can measure inward. So let the scale shrink slowly, let precision soften into meaning, and allow the smallest possible measurement to come into focus. Human beings have a habit of dividing things. A loaf of bread becomes slices, a field becomes plots, a day becomes hours, minutes, seconds. Space follows the same instinct. A room can be measured corner to corner. A street can be paced out step by step. A journey can be broken into miles, then yards, then inches, until distance feels fully tamed by numbers. This habit feels so natural that it is rarely questioned. If something feels too large, it can be divided. If something feels too coarse, it can be measured more finely. The assumption sits quietly in the background of everyday life. Space, it seems, can always be split again, and again, and again. At familiar scales, this works beautifully. A human hair can be measured across its width. Zoom in further, and the hair becomes a bundle of fibres. Look closer still, and those fibres resolve into molecules arranged in long chains. The idea of endless division feels not only reasonable but obvious. Each level simply reveals another layer beneath it. For a long time, science shared this comfort. Early measurements dealt with what the senses could reach: rulers, calipers, pendulums, lenses. As tools improved, so did confidence. Distance shrank, precision increased, and the world revealed structure after structure hidden inside what once looked solid and smooth. The 20th century pushed this process far beyond everyday intuition. Atoms, once thought to be indivisible, were found to contain smaller parts. Electrons, protons, and neutrons entered the picture. Then protons and neutrons themselves revealed internal structure. Quarks, fields, interactions. Each discovery encouraged the same quiet assumption. If this can be divided, then surely something smaller lies beneath. But something subtle begins to change as scale shrinks. At the atomic level, measurement no longer feels passive. To observe an electron is not like measuring the width of a table. Observation becomes an interaction. Energy must be exchanged. The act of looking leaves a trace. Distance is no longer just something that exists. It is something that must be carefully defined. As measurements push into smaller and smaller regimes, this effect grows stronger. At subatomic scales, precision comes at a cost. To resolve a smaller distance, higher energy is required. This is not a technological inconvenience. It is a physical rule. Probing smaller structures means concentrating more energy into a smaller region of space. For a while, physics adapts. Quantum mechanics provides a framework for handling uncertainty. Probabilities replace certainties. Fields replace solid objects. Distance is still meaningful, but it becomes fuzzier, less absolute. Still, the underlying question remains mostly unspoken. Can this process continue forever? Can space be divided endlessly, with each smaller scale revealing yet another layer beneath it? Or is there a point where the very idea of dividing distance stops making sense? This question does not arise from philosophy alone. It emerges naturally when different parts of physics are brought together. Quantum mechanics governs the small. Relativity governs gravity and spacetime. Each works extraordinarily well within its own domain. But when both are applied at once, something curious happens. As distances shrink and energies rise, gravity refuses to remain negligible. At everyday scales, gravity is weak. At planetary scales, it shapes orbits. At cosmic scales, it sculpts galaxies. At extreme energies concentrated into tiny regions, gravity becomes impossible to ignore. Space itself responds. If enough energy is packed into a sufficiently small region, spacetime curves dramatically. Push this idea far enough, and familiar descriptions break down entirely. Attempts to measure smaller distances begin to disturb the structure of space itself. The ruler bends. The measuring act reshapes what is being measured. This is where physics begins to hesitate. Not because it runs out of mathematics, but because concepts start to overlap in uncomfortable ways. Distance, energy, gravity, and quantum uncertainty refuse to stay neatly separated. The assumption of endless division begins to look less like a certainty and more like a habit. Out of this tension emerges a particular scale, not chosen by convention and not discovered by experiment, but implied by the structure of physical law, a length that combines the speed at which information travels, the strength of gravity, and the fundamental graininess of quantum action. When written down, this length is astonishingly small. This scale is known as the Planck length. To appreciate this gently, it helps to resist comparison for a moment. This number is not meant to be imagined directly. It does not describe an object, or a particle, or a tiny bead of space. It describes a limit, a point at which the usual language of measurement begins to lose its footing. The Planck length is not a smallest piece of space in the way a brick is the smallest piece of a wall. It is not a boundary you could reach by shrinking yourself. Instead, it marks the scale at which asking for a smaller distance no longer produces a clearer answer. The question itself begins to wobble. Physicists often describe this as a conceptual boundary rather than a physical wall. Nothing slams into it, nothing bounces off. Instead, familiar ideas simply stop applying cleanly. The rules that allow distances to be compared, subdivided, and measured cease to work together in a consistent way. This distinction matters. A wall implies something solid and absolute. A boundary of meaning is quieter and more subtle. It suggests that reality may continue beyond our descriptions, even if those descriptions can no longer follow. The Planck length does not say space ends here, it says measurement does. Historically, this idea traces back to the early 20th century, when physicists like Max Planck noticed that certain combinations of fundamental constants produced natural units of length, time, and mass. These units did not depend on human conventions like meters or seconds. They arose from nature itself. At the time, this was a mathematical curiosity. Only later did it become clear how deeply these scales are woven into the structure of physical law. As quantum theory matured and relativity reshaped understanding of spacetime, the Planck length began to look less like an abstract construction and more like a signpost. Modern physics does not claim to fully understand what happens at this scale. Different theories offer different pictures. Some suggest spacetime becomes grainy. Others suggest it remains smooth but unpredictable. What they share is agreement that something fundamental changes here, and that agreement is striking. Independent lines of reasoning, developed for entirely different purposes, all point toward the same scale, not as an answer, but as a warning. Below this, proceed with caution. There is something quietly humbling about this idea. Human beings have built machines that peer billions of years into the past, detectors that catch particles passing unnoticed through the Earth, telescopes that map galaxies at the edge of the observable universe. And yet, at the opposite extreme, there appears to be a limit we cannot cross even in principle. This is not failure, it is information. The idea of a smallest meaningful scale reshapes how distance itself is understood. It suggests that space is not merely an empty stage on which events unfold, but an active participant with its own structure and rules that allow division up to a point, and then gently refuse further refinement. In that sense, the Planck length is less about how small things are, and more about how nature communicates. It marks the scale at which the universe stops answering certain questions in the language that has worked everywhere else. And rather than closing doors, that realization opens new ones. Because once it becomes clear that endless division is not guaranteed, a deeper question takes its place. If measurement has a limit, what does that say about space itself? Once the idea of a smallest meaningful scale enters the conversation, a natural question follows. Where does that scale come from? Why this length, and not another? Why does nature appear to hesitate at this particular point, instead of allowing distance to shrink without limit? The answer is quietly elegant. The Planck length is not something physicists stumbled upon by accident, and it is not the result of fitting data to a curve. It emerges when three of the deepest features of reality are allowed to speak at the same time: gravity, quantum behaviour, and the structure of space-time itself. Each of these governs a different aspect of the universe. Gravity shapes how mass and energy curve space. Quantum mechanics governs how matter and energy behave at very small scales. Relativity sets the rules for space, time, and the speed at which information can travel. For most practical purposes, these ideas operate in separate domains. But when questions are pushed to extremes, separation becomes impossible. To understand how this works, it helps to step back to the early 20th century. Physics was in the middle of a quiet revolution. Classical ideas were straining under new experimental results, and familiar assumptions were beginning to crack. In this atmosphere, a German physicist named Max Planck began thinking about something deceptively simple: units. At the time, measurement systems were entirely human inventions. Meters came from the size of the Earth, seconds from the rotation of the planet, kilograms from carefully preserved objects in vaults, useful, practical, but deeply parochial. They reflected human convenience, not universal law. Planck wondered whether nature itself might offer a more fundamental set of units. Units that would make sense anywhere in the universe, regardless of culture, planet, or species. Units built not from human history, but from physical constants that appear to be woven into reality itself. To do this, Planck focused on three quantities that seemed unavoidable. First, the speed at which information travels through space. This speed is not just about light. It is a limit built into spacetime itself. No signal, no cause, no influence can outrun it. It sets the structure of cause and effect across the universe. Second, the constant that governs quantum behaviour. This quantity sets the scale at which energy comes in discrete packets, rather than flowing smoothly. It determines how much action is involved when something happens at the smallest scales. Without it, quantum mechanics collapses back into classical physics. Third, the strength of gravity. Gravity is often the odd one out in physics. Weak at everyday scales, yet dominant across cosmic distances. It governs how mass and energy shape space and time, and it refuses to be ignored when enough energy is concentrated into a small region. Individually, each of these constants defines a domain. Together they define a meeting point. When they are combined in just the right way, a length naturally appears, not by choice, but by necessity. A scale at which quantum effects, gravity, and space-time geometry are all equally important. That scale is the Planck length. It is crucial to emphasize that nothing arbitrary happens here. No one decided that this length should matter. It simply falls out of the mathematics when these three aspects of nature are taken seriously at once. Remove any one of them, and the scale disappears. Include all three, and the scale is unavoidable. This is why the Planck length feels different from other extreme numbers in physics. It is not merely small, it is structurally significant. It represents the point where familiar descriptions stop working, not because they are wrong, but because they are incomplete. When physicists calculate this length, they are not predicting a physical object of that size. They are identifying a threshold. Below this scale, attempts to localize events require so much energy that gravity itself becomes disruptive. Space responds. Time responds. The measuring process begins to undermine its own assumptions. At this point, it becomes impossible to talk about distance in the usual way. The very act of defining a smaller length demands conditions that would warp space-time beyond recognition. This is not a technological problem. It is a conceptual one. And this is why the Planck length is often described as a limit of meaning rather than a limit of size. It does not say that space stops existing below a certain scale. It says that the language used to describe space loses coherence. When expressed numerically, this length comes out to 1.6 times 10 to the minus 35 meters. That value is not important because of its precision. It is important because of what it represents. A balance point between the universe's most fundamental rules. There is a quiet humour hiding in this idea. Nature, it seems, insists on setting its own measuring stick. No matter how refined human instruments become, no matter how clever the techniques, there appears to be a scale beyond which the universe politely declines further interrogation. Not out of secrecy, but out of consistency. It is tempting to imagine this length as a tiny grain of space, like a pixel on a cosmic screen. But that image can mislead. The Planck length is not a building block. It is not something space is made of in the way atoms make up matter. It is better understood as a boundary condition, a signal that certain questions must be asked differently. The elegance of this result is part of what makes it so compelling. Three constants, discovered for entirely different reasons, converge on the same scale. The speed of light emerged from electromagnetism, quantum action from blackbody radiation, gravity from planetary motion and falling apples, and yet, at the deepest level, they appear to conspire. This convergence suggests that the Planck length is not an accident of theory, but a reflection of something real about the universe. Even if current physics cannot fully describe what happens at this scale, the scale itself appears unavoidable. Modern theoretical physics continues to explore this territory cautiously. Different approaches attempt to describe spacetime near the Planck length in different ways. Some imagine fluctuations, some imagine networks, some imagine entirely new mathematical structures. What unites them is the recognition that ordinary concepts of distance cannot simply be extended indefinitely. In this sense, the Planck length is less like a destination and more like a warning sign. It does not tell us what lies beyond. It tells us that our usual tools are no longer sufficient, that new ways of thinking will be required, and that may be its most important role. By emerging naturally from the deepest principles known, the Planck length quietly reminds physics of its own limits, not as a failure, but as an invitation to refine language, to rethink assumptions, and to accept that nature sets the terms of measurement, not the other way around. If space truly has a smallest meaningful scale, then that scale was never chosen by humans. It was written into the universe long before rulers, numbers, or questions existed. There is a quiet assumption woven into everyday thinking. If something exists, it can be measured. If it cannot be measured, it must be vague, imaginary, or not fully real. This idea feels so natural that it often goes unnoticed. From childhood, the world is introduced through rulers, clocks, scales, and numbers: height, weight, distance, duration. Reality arrives already quantified. Science, too, is built on this foundation. Physics in particular relies on measurement as its primary language. Distances are compared, times are recorded, energies are calculated. Without measurement, patterns remain hidden, and predictions fall apart. Measurement turns observation into knowledge. Yet measurement is not the same thing as existence. This difference matters more than it first appears. Long before modern physics, there were things that clearly existed but could not be measured. The warmth of sunlight, the heaviness of air, the passage of time itself. These were experienced directly, but resisted precise description. Over centuries, tools improved, and these experiences slowly became quantities. Temperature acquired degrees, air gained pressure, time gained seconds. This success quietly reinforced the belief that everything real can eventually be measured, given enough ingenuity and patience. If a phenomenon resisted quantification, it was assumed to be a temporary problem, a missing instrument, an incomplete theory. Physics has been extraordinarily effective under this assumption. From the motion of planets to the vibrations of atoms, the measurable world expanded dramatically. Each success strengthened confidence that reality and measurement marched together, step for step. But as measurement pushed into more extreme regimes, cracks began to show. At very small scales, measurement stopped behaving like a passive act. To measure something tiny, energy must be involved. Light must scatter. Fields must interact. Probes must disturb what they touch. The smaller the target, the more disruptive the measurement becomes. This is not a philosophical complaint. It is a physical rule. Precision demands energy. And energy, when concentrated, has consequences. Quantum mechanics formalized this insight. It showed that certain pairs of properties cannot be pinned down simultaneously with unlimited accuracy. This is not due to clumsy instruments or human error. It is built into the structure of nature. The universe itself places limits on what can be known at once. Even so, measurement remains meaningful in this domain. Probabilities replace certainties, but distances and times can still be discussed. Reality becomes fuzzy, not inaccessible. The real tension appears when gravity enters the picture. As distances shrink further, the energy required to probe them rises sharply. At some point, that energy becomes large enough for gravity to matter in a dramatic way. Space itself responds to the attempt to measure it. Curvature increases. Time slows. The measuring process begins to reshape the stage on which it is performed. This is where the Planck length takes on a deeper significance. Attempts to define smaller distances run into a fundamental problem. The very tools required to make the measurement would so strongly disturb spacetime that the notion of a clean distance breaks down, not because reality disappears, but because measurement loses its footing. This distinction is subtle, but crucial. The Planck length does not say that nothing exists below this scale. It says that the concept of distance, as normally defined, may no longer apply. The map stops matching the territory, not because the territory ends, but because the map was never designed for that terrain. Physics depends on measurement because measurement provides shared reference points. A distance that can be measured can be compared, tested, and communicated. It can be checked by different observers using different tools. Measurement anchors knowledge in a common framework. But that framework has assumptions built into it. It assumes that space-time behaves smoothly, that events can be separated cleanly, that cause and effect unfold against a stable background. At everyday scales, these assumptions hold extremely well. At the Planck scale, they begin to wobble. This does not mean that physics suddenly becomes meaningless. It means that the questions being asked must change. Asking for ever smaller distances using the same conceptual tools may be like trying to measure temperature with a ruler. The tool is precise, but the question is mismatched. There is a quiet temptation to equate measurability with reality. If something cannot be measured, it is tempting to treat it as non-existent. But physics itself suggests caution here. Fields existed before they could be detected. Waves existed before they could be recorded. Even atoms were once hypothetical, inferred long before they were seen. The inability to measure directly has never been a reliable guide to what exists. It has only ever marked the boundary of current methods. The Planck length pushes this idea further. It suggests a boundary not just of technology, but of conceptual clarity. A place where asking for a more precise distance no longer sharpens understanding, but muddies it. This challenges a deeply ingrained intuition. The idea that reality must always be divisible, always countable, always expressible in smaller units. It suggests instead that some aspects of the universe may resist infinite refinement. Importantly, this resistance does not imply chaos or arbitrariness. The Planck length is not a random cutoff. It emerges from the most carefully tested principles in physics. Relativity, quantum mechanics, and gravity all point toward the same conclusion when pushed together. That convergence lends weight to the idea that measurement, not reality, is what runs out. In this view, the universe may continue smoothly below the Planck scale, or it may behave in unfamiliar ways. Current physics does not yet say. What it does say is that the language of distance, as presently understood, cannot simply be extended downward forever. There is something quietly liberating about this. It means that physics is not failing when it reaches such limits. It is succeeding. It is identifying the edges of its own applicability. Science advances not only by answering questions, but by learning which questions need to be rephrased. The Planck length represents one of those moments, a signal that the relationship between measurement and reality is more delicate than it first appears. Measurement remains indispensable. Without it, physics dissolves into speculation. But measurement is a tool, not a mirror. It captures aspects of reality, not its entirety. At familiar scales, the difference is negligible. At extreme scales, it becomes profound. The Planck length invites a gentle humility, a recognition that reality is not obligated to fit perfectly into human categories, that there may be aspects of the universe which exist, influence, and matter, even if they cannot be pinned down with numbers in the usual way. This is not a retreat into mystery for its own sake. It is an acknowledgement of depth, a recognition that the universe may be richer than the questions currently used to describe it. In that sense, the Planck length does not shrink reality, it expands it. By marking the limits of measurement, it hints at dimensions of existence that lie beyond the reach of rulers and clocks, waiting not for smaller instruments, but for new ways of understanding. At first glance, it feels obvious that seeing smaller should simply mean building better tools, a stronger microscope, a sharper beam, a more refined detector. If detail is missing, the instinct is to increase resolution, the way a photograph improves when more pixels are added. This logic works beautifully at familiar scales. A magnifying glass reveals details the eye cannot see. A microscope opens up entire hidden worlds inside a drop of water. Each improvement brings clarity, not complication. Smaller feels better, more precise feels safer, but this intuition begins to bend as scale shrinks. In everyday life, observation is gentle. Looking at a chair does not change its shape. Measuring a table does not warm it. At small scales, observation becomes less polite. To see something tiny, it must be interacted with. Light must bounce, energy must be exchanged, and that exchange always leaves a mark. The smaller the detail being probed, the more energetic the probe must be. This is not a preference, it is a rule woven into how waves behave. Shorter distances require shorter wavelengths, and shorter wavelengths carry higher energy. Precision comes with intensity attached. At first, this trade-off is manageable. At atomic scales, energetic probes disturb electrons, but the disturbance can be accounted for. Measurements become probabilistic rather than exact, but they remain meaningful. Physics adjusts its expectations and continues. As distance shrinks further, the cost rises sharply. Trying to examine extremely small regions is like trying to feel the texture of a spider's web while wearing thick gloves. Press harder, and the web deforms. Press even harder, and it snaps. The problem is not poor technique. It is that the act of inspection overwhelms the thing being inspected. At extreme scales, this is no longer a metaphor. Concentrating large amounts of energy into a tiny region does not just disturb particles, it disturbs space itself. Gravity, usually the quiet background force of the universe, suddenly becomes impossible to ignore. Energy has weight. Energy curves space-time. Pack enough of it into a small enough volume, and space responds dramatically. This introduces a surprising twist. The better the attempt to measure a tiny distance, the more that distance becomes distorted. Precision starts to undermine itself. Imagine trying to map the surface of a pond by throwing stones into it. Small pebbles create gentle ripples that reveal the surface shape. Larger stones create waves that obscure it. At some point, adding more force does not improve the picture. It destroys it. Physics suggests that this self-defeating behaviour becomes unavoidable. Attempts to probe smaller distances require energy so extreme that space-time itself would be violently disturbed. The measuring process would overwhelm the concept of distance it is trying to define. This is where the phrase "smaller is better" quietly loses its authority. The Planck length does not represent a failure of imagination or technology. It reflects a deeper principle. That measurement is an interaction, and interactions have consequences. When those consequences become larger than the thing being measured, clarity gives way to distortion. This idea can feel unsettling at first. It seems to suggest a barrier, a limit, a door closing. But there is another way to see it. Limits in physics often signal structure, not restriction. The speed of light does not prevent motion. It defines how motion works. Absolute zero does not forbid temperature. It clarifies what temperature means. In the same way, a smallest meaningful length does not forbid reality below it. It defines where certain descriptions stop being useful. Rather than imagining the Planck length as a wall, it helps to think of it as a change in language. Above it, distance behaves like something that can be sliced thinner and thinner. Below it, the universe may still exist, but the familiar vocabulary of measurement no longer applies cleanly. There is also a gentle reassurance hidden in this idea. Nature is not withholding information out of stubbornness, it is maintaining consistency. The same rules that allow measurement to work so well at larger scales are the ones that quietly prevent it from being pushed beyond coherence. Curiosity does not end here, it changes shape. Physicists do not stop asking questions at this scale, they ask different ones. Instead of demanding sharper rulers, they look for new frameworks, new ways of describing what happens when space, time, energy, and gravity are inseparable. This shift mirrors other moments in scientific history. When speed approached the speed of light, classical mechanics did not fail. It was absorbed into a broader picture. When atoms defied classical expectations, physics did not collapse. It evolved. The Planck length invites a similar transition. Not panic, not resignation, just patience. There is a subtle comfort in knowing that the universe does not reward brute force curiosity indefinitely, that pushing harder is not always the path to understanding. Sometimes restraint reveals more than pressure. Smaller is not always better because understanding is not about domination. It is about alignment. When questions are tuned to the structure of reality, answers emerge naturally. When they are forced beyond that structure, noise takes over. Seen this way, the Planck length is not a warning sign. It is a guidepost, a reminder that the universe has its own scales of cooperation. Work with them, and clarity follows. Fight them, and confusion grows. Calm curiosity thrives here, not anxious urgency. The smallest scales are not demanding conquest, they are inviting patience. And in that patience, physics continues to listen, rather than insist. At everyday scales, space feels dependable. A room remains the same size whether it is measured once or 100 times. A distance does not flicker or hesitate. It simply exists, waiting to be crossed, mapped, or ignored. This reliability is so familiar that it is rarely questioned. Space feels like a quiet backdrop, indifferent to observation. Quantum physics gently unsettles that comfort. In the quantum world, uncertainty is not a flaw in measurement. It is a feature of reality. Certain properties refuse to settle into fixed values all at once. Position and motion blur together. Energy fluctuates. Outcomes become probabilistic rather than definite. This behaviour is not due to faulty instruments, but to how nature behaves when examined closely. For particles and fields, this uncertainty is well established, but when the same idea is extended to space itself, things become far more subtle. The usual picture of space imagines it as a kind of grid, points laid out neatly, distances connecting them cleanly. Even when space is curved by gravity, as described by relativity, it is still treated as smooth, stretchable, bendable, but continuous and well-defined at every point. At extremely small scales, that picture may begin to dissolve. When physicists apply quantum principles to space-time, they find that space may not sit still. Instead of a rigid scaffold, it may behave more like a restless surface, gently rippling, briefly fluctuating, never violent but never perfectly calm either. These fluctuations are not motions through space, they are fluctuations of space. The idea can feel strange because everyday experience offers no direct analogy. But a few gentle images can help. Imagine the surface of the ocean viewed from a great height. It looks smooth and uniform. Zoom in and small waves appear. Zoom further and the surface becomes lively with ripples, eddies and shifting patterns. The water itself has not changed. Only the scale of observation has. Some physicists suspect that spacetime behaves in a similar way. At large scales, it appears smooth and continuous. At very small scales, it may reveal a subtle restlessness, tiny fluctuations in geometry, fleeting variations in distance, not enough to disrupt everyday physics, but enough to matter near the smallest meaningful scales. This is not a settled picture. It is a cautious proposal supported by multiple lines of reasoning, rather than direct observation. The energies required to probe such behaviour lie far beyond what current experiments can reach. So the discussion remains theoretical, guided by consistency rather than measurement. What lends weight to this idea is how naturally it arises when quantum uncertainty and gravity are taken together. Quantum mechanics allows energy to fluctuate briefly, even in empty space. These fluctuations are normally tiny and fleeting, but energy influences gravity, and gravity influences the shape of space-time. At ordinary scales, the effect is negligible. At extreme scales, it may not be. Near the Planck length, these effects can no longer be ignored. The energy involved in probing such distances is so large that gravitational effects become inseparable from quantum behaviour. Space itself may fluctuate simply because the laws governing energy and uncertainty demand it. This leads to an image of space-time that is less like a fixed grid and more like a living texture, not chaotic, not random, but dynamic in a quiet, constant way. Distances may not have single, sharply defined values at every instant. Instead, they may hover within small ranges, shaped by underlying uncertainty. It is important to be careful here. Physics does not claim that space dissolves into chaos at small scales, nor does it suggest that geometry becomes meaningless. Rather, it suggests that the familiar idea of precise, sharply defined distances may no longer apply. This is a subtle shift, not a dramatic collapse. In many approaches to quantum gravity, space-time remains well behaved on average. Over larger scales, the fluctuations smooth out. The restless surface becomes calm again. This helps explain why classical physics works so well everywhere we can test it. Only when distances approach the Planck scale do these fluctuations become significant. That scale, around 1.6 times 10 to the minus 35 meters, marks the point where uncertainty in spacetime itself may become unavoidable. Below it, the notion of a single, precise distance may no longer be meaningful in the usual sense. This does not mean that reality becomes unknowable. It means that knowledge must be expressed differently. Instead of asking for exact distances, physics may need to describe ranges, probabilities, statistical behaviours, patterns that emerge when uncertainty is taken seriously rather than resisted. There's a gentle irony here. The same quantum principles that allow extraordinary precision in technologies like atomic clocks may also impose limits at the deeper scales. Precision and uncertainty are not opposites. They are partners, each defining the other. Historically, this way of thinking did not emerge overnight. It developed gradually as physicists learned to trust the implications of their own theories. Figures like Werner Heisenberg show that uncertainty was not a temporary inconvenience, but a permanent feature of the quantum world. Extending that insight to space-time itself is a natural, though challenging next step. Still, caution remains essential. No experiment has yet observed quantum fluctuations of space-time directly. Current understanding is guided by mathematical consistency, not empirical confirmation. Different theories offer different pictures, and none can yet claim authority. Some suggest space-time fluctuations resemble gentle foam. Others imagine networks or discrete relationships. Some propose that space remains smooth but unpredictable. What unites these ideas is not agreement on details, but agreement that the classical image of perfectly fixed distances cannot survive unchanged at extreme scales. This uncertainty should not be mistaken for weakness. It reflects honesty. Physics progresses by admitting what it does not yet know, and by carefully marking the boundaries of established understanding. The Planck scale sits squarely at such a boundary. Beyond it, speculation becomes unavoidable, but it is disciplined speculation, constrained by what is already known. For listeners, there is no need to picture these fluctuations vividly. They are not something to imagine visually so much as something to accept conceptually. Space may be quieter than the ocean, but it may not be perfectly still, and that is a deeply calming thought. Rather than being a rigid, lifeless stage, the universe may possess a subtle texture even at its foundation, a gentle dynamism that allows structure, motion, and change to exist at all scales. Uncertainty in this sense is not a flaw, it is a sign of depth. When space becomes uncertain, it does not fall apart. It reveals that the universe is richer than the simplest pictures allow, that beneath smooth appearances lies a quiet complexity, not demanding fear or urgency, but inviting patience. At the smallest scales, certainty softens, precision relaxes, and space itself may breathe, not in dramatic pulses, but in subtle, persistent motion. Understanding this is not about reaching a final answer. It is about learning to ask better questions, and allowing uncertainty to be part of the landscape, rather than something to be eliminated. In that quiet acceptance, physics continues its slow, careful exploration of the deeper structure of reality. When space begins to lose its sharp edges, time is never far behind. The two are woven together so tightly that changes in one inevitably echo in the other. This is not a poetic statement. It is a physical one. Space and time are not separate stages on which the universe performs. They are part of the same fabric. At everyday scales, time feels steady and dependable. Seconds tick forward. Clocks agree with one another. Cause follows effect in a neat, orderly way. Even when time feels slow or fast subjectively, its measurement remains consistent. A second is a second wherever it happens. Physics reinforces this comfort. Time can be divided cleanly. Minutes become seconds. Seconds become fractions. Modern clocks can track intervals far shorter than anything the human body could sense. Time, like space, seems endlessly divisible. But just as with distance, this assumption begins to wobble at extreme scales. The deep link between space and time became unmistakable in the early 20th century, when physicists realized that motion, gravity, and measurement could not be fully described without treating them together. Space could stretch, time could slow. Events that seemed simultaneous to one observer might not be to another. The universe did not offer a single, universal clock. This insight reshaped physics completely. Space and time merged into space-time. Distances and durations became two sides of the same structure. Change one, and the other responds. So when physics begins to ask whether there is a smallest meaningful distance, it is natural to ask a parallel question. Is there also a smallest meaningful interval of time? That question leads to a related concept known as Planck time. Just as the Planck length emerges from combining gravity, quantum behaviour, and space-time structure, Planck time emerges from the same ingredients. It represents the time it would take light to travel one Planck length in a vacuum. Not because light is special in a poetic sense, but because it represents the fastest way information can move. When calculated, this interval comes out to about 5.4 times 10 to the minus 44 seconds. As with the Planck length, this number is not meant to be imagined directly. It is not a tiny tick of a cosmic clock. It is a boundary of meaning, a scale at which the usual idea of time as a smooth-flowing parameter may no longer apply. This does not mean that time stops below this interval. It means that asking for smaller and smaller slices of time may cease to produce clearer descriptions. To understand why, it helps to return to the relationship between measurement and interaction. Measuring time always involves change. A clock counts oscillations, a particle decays, a signal travels. Each of these processes depends on physical interactions unfolding within space-time. To measure shorter intervals, faster processes and higher energies are required. At extreme scales, the energy involved in defining very short durations begins to disturb the system being measured. And because energy influences gravity, space-time itself becomes involved. This mirrors what happens with distance. Attempts to define extremely small time intervals demand conditions so extreme that space-time responds dynamically. The background becomes part of the experiment. As a result, the notion of a sharply defined instant may begin to blur. Some physicists describe this as time becoming uncertain at the smallest scales. Not in the everyday sense of clocks being imprecise, but in a deeper sense. The universe may not permit events to be ordered more finely than a certain limit using familiar concepts. This idea can feel unsettling, because time plays such a central role in human experience. It governs memory, anticipation, and causality itself. The thought that time might not be infinitely divisible can sound like a challenge to common sense. But here, as elsewhere, physics encourages restraint rather than alarm. The Planck time does not claim to be the smallest moment that exists. It marks the scale at which current theories can no longer describe time as a smooth parameter, independent of the processes used to measure it. The limit applies to knowledge, not necessarily to reality. This distinction matters deeply. Throughout the history of science, limits on measurement have often been mistaken for limits on existence. Atoms existed long before they could be resolved. Gravitational waves rippled through space long before detectors could sense them. Reality has never waited for instruments. The Planck time fits this pattern. It tells physics how far its current language can go. It does not tell the universe how to behave. In many theoretical approaches, space-time remains well behaved on average, even at these scales. Fluctuations may occur, but they do not erase structure. Over larger intervals, time flows smoothly again. Causality holds. Events remain ordered. Only when attention is focused too narrowly does the description begin to fray. This perspective helps keep the discussion grounded. There's no need to imagine time shattering into chaos or flickering randomly. There's no evidence for that. What there is instead is a recognition that the tools used to describe time may lose precision when pushed beyond their natural range. This is not unique to physics. Language itself has limits. Colours fade into one another. Concepts blur at extremes. Precision gives way to approximation. Time may behave in a similar way, smooth and reliable where it matters most, subtle and elusive at depths far removed from experience. There is a gentle humour in this. Human beings, after all, evolved to track days, seasons, and lifetimes, not intervals shorter than anything that could ever be sensed. The universe may simply decline to answer questions that were never meant to be asked in quite that way. Importantly, none of this diminishes the success of physics. On the contrary, it highlights its strength. Physics is not claiming certainty where none exists. It is carefully marking the boundaries of its own applicability. The Planck time stands alongside the Planck length as a signpost. Together they indicate that space-time itself may have a scale beyond which familiar descriptions lose clarity. Not abruptly, not catastrophically but gently. Space becomes uncertain. Time follows. And yet at all scales accessible to experiment, time behaves beautifully. Clocks remain astonishingly precise. Predictions remain reliable. The universe remains consistent. This balance is worth appreciating. Limits at extreme scales do not undermine everyday reality. They support it. They allow structure, stability, and predictability to emerge where they're needed most. Seen this way, the smallest scales are not threatening. They are reassuring. They suggest that the universe is not infinitely fragile, nor infinitely sharp. It has depth, texture, and tolerance. Time, like space, appears to have a domain where questions must be asked differently, where measurement softens into description, where precision gives way to pattern, and that is not a loss. It is a reminder that reality is richer than any single way of measuring it. At the smallest scales, time may not tick in the way clocks imagine, but above those scales, it flows with extraordinary reliability. Enough to build stars, enough to build life, enough to tell stories. And for now, that is more than enough. For most of everyday life, gravity feels almost modest. It keeps feet on the ground, holds oceans in place, and nudges falling objects toward the floor. Compared to other forces of nature, it seems gentle, even polite. A small magnet can lift a paperclip against the pull of the entire Earth. A static charge can defy gravity with ease. Because of this, gravity is often treated as a background presence. Important, yes, but rarely dominant at small scales. When physicists study atoms, particles, and quantum effects, gravity usually stays out of the way. Its influence is so weak that it can be safely ignored. This comfortable separation holds for an astonishing range of situations. From the chemistry of life to the workings of particle accelerators, gravity barely registers. Quantum physics handles the small, gravity handles the large. Each stays mostly in its own lane. But nature does not promise eternal separation. As attention turns toward the smallest meaningful scales, gravity quietly re-enters the conversation. Not because it grows stronger in an absolute sense, but because everything else is being pushed to extremes. The reason is subtle. Probing smaller distances requires higher energies. Concentrating energy into tiny regions is the price of precision. And energy, according to relativity, is not just a bookkeeping tool. It has weight. It bends space-time. It acts as a source of gravity. At everyday scales, this effect is negligible. The energy involved in measurement is far too small to noticeably curve space. But as distances shrink toward the Planck scale, the energies involved rise to extraordinary levels. Gravity can no longer be ignored. The act of measurement itself becomes gravitationally significant. Space is no longer a passive stage. It responds. This is where familiar divisions in physics begin to blur. Quantum mechanics describes the behaviour of matter and energy at small scales with extraordinary accuracy. It embraces uncertainty, probability, and discreteness. Gravity, on the other hand, is described by a theory that treats space-time as smooth and continuous, responding gracefully to mass and energy. Each theory works remarkably well within its own domain. Each has been tested extensively. Each has earned deep confidence. The problem arises when both are needed at the same time. At the Planck scale, quantum effects and gravitational effects are equally important. Ignoring either one leads to incomplete or inconsistent descriptions. But combining them has proven profoundly difficult. This is not for lack of effort. For decades, physicists have tried to bring gravity into the quantum framework, or to reformulate quantum physics in a way that naturally includes gravity. Progress has been made, but no single approach has yet achieved the same level of experimental confirmation as existing theories. One reason for this difficulty lies in how differently the two frameworks treat reality. Quantum physics thrives on uncertainty. It allows quantities to fluctuate. It describes outcomes in terms of probabilities. Gravity, as currently understood, does not like uncertainty. It treats spacetime as a well-defined geometric object. Smooth, continuous, deterministic. Trying to quantize gravity is like trying to make a calm surface behave like a cloud of probabilities without tearing it apart. The mathematics resist simple solutions. The concepts strain against one another. At the Planck scale, these tensions can no longer be postponed. The energies involved force gravity and quantum behaviour into direct contact. Space fluctuates. Time hesitates. Measurement becomes entangled with geometry. Existing theories struggle here not because they are wrong, but because they were never designed for this regime. Quantum mechanics was built to explain atoms, light, and particles. Relativity was built to explain gravity, motion, and cosmic structure. Each excels in its own territory. The Planck scale sits at their overlap, where neither can be applied in isolation. This is why the Planck length carries such weight in theoretical physics. It marks the scale where gravity stops being optional in discussions of the very small. At this scale, even empty space is no longer empty in a simple sense. Energy fluctuations permitted by quantum principles carry gravitational consequences. Space-time itself becomes a participant rather than a backdrop. It is tempting to imagine gravity suddenly becoming violent or chaotic here. That is not what current understanding suggests. The issue is not turbulence, but incompatibility. The smooth language of geometry and the probabilistic language of quantum theory begin to talk past each other. Different research programs attempt to bridge this gap in different ways. Some try to describe space-time as emerging from more fundamental relationships. Others attempt to quantize geometry itself. Still others explore entirely new mathematical frameworks. What unites these efforts is caution. There is no experimental data yet that directly probes the Planck scale. The energies required lie far beyond what any current or foreseeable accelerator can produce. As a result, theory must be guided by consistency, not confirmation. This is where humility becomes essential. Physics has earned its confidence through centuries of success, but it has also learned the cost of overconfidence. History is filled with moments when certainty gave way to surprise. Each time, progress came not from insisting on old frameworks, but from letting them evolve. The Planck scale reminds physicists that even the most trusted theories have limits. Not limits of validity, but limits of reach. They describe nature extraordinarily well where they apply. They do not claim authority everywhere. There is something quietly reassuring in this restraint. Rather than pretending to know what happens when gravity and quantum effects collide fully, physics marks the boundary and proceeds carefully. Speculation is disciplined. Claims are modest. Unknowns are acknowledged openly. Gravity's reappearance at the smallest scales does not undermine previous successes. It completes the picture. It shows that forces cannot be neatly separated forever, that the universe resists being partitioned into isolated domains. In this sense, gravity does not barge into the quantum world. It waits patiently until it can no longer be ignored. And when it does appear, it does so not as a threat, but as a reminder that nature is unified, that the same force guiding galaxies also shapes the deepest limits of measurement. At the Planck scale, gravity becomes dominant not because it grows louder, but because everything else is being pushed so far that its quiet influence can no longer be set aside. This dominance does not signal an endpoint, it signals a frontier, a place where understanding slows, questions become more careful, and certainty gives way to curiosity. A place where physics listens as much as it speaks. The conversation between gravity and quantum physics is still ongoing. No final resolution has been reached, and that is exactly as it should be. Science advances not by forcing answers where evidence is thin, but by respecting the boundaries of what is known. At the smallest scales, gravity reminds physics of that discipline. It asks for patience, for precision, and for the humility to admit that the universe may still have lessons left to teach. As the Planck length comes into focus, physics reaches a familiar but delicate moment. A place where equations still work, but their interpretations begin to fray. A place where confidence gives way not to confusion, but to caution. This is often described as the edge of known physics. The phrase can sound dramatic, but its meaning is precise. It does not imply a cliff or a void. It refers to the boundary where existing theories stop providing reliable descriptions, not because reality disappears, but because the tools used to describe it were never meant to operate there. The Planck length sits squarely at this boundary. For distances larger than the Planck length, physics functions extraordinarily well. Quantum mechanics predicts particle behaviour with astonishing accuracy. Relativity describes gravity and spacetime with elegant precision. Experiments confirm predictions again and again. Confidence is earned, not assumed. As distances shrink toward this scale, something subtle changes. The theories do not suddenly contradict themselves. They do not collapse into nonsense. Instead, they begin to talk past one another. Quantum mechanics assumes a fixed spacetime background. Relativity insists that spacetime itself is dynamic, shaped by energy and momentum. Each assumption works beautifully in isolation. At the Planck scale, both must apply simultaneously, and neither is fully equipped for the task. This is what physicists mean when they speak of a breakdown. Breakdown does not mean failure in the everyday sense. It does not mean that equations become useless, or that predictions turn false. It means that the assumptions underpinning those equations are no longer compatible when pushed into a regime they were never designed to describe. A helpful analogy comes from cartography. A map of a city works wonderfully for navigating streets. It tells you where roads intersect, where bridges cross, where distances matter. But use that same map to navigate the ocean floor and it fails. Not because it is wrong, but because it is incomplete. It was never meant for that terrain. Physics encounters a similar situation at the Planck scale. The theories that describe particles and forces were developed using experiments that operate far above this scale. Their success is immense, but it is contextual. When they are extended downward without modification, inconsistencies appear. Not contradictions, but ambiguities. Not errors, but unanswered questions. This distinction matters deeply. Science progresses by identifying exactly where its descriptions stop working cleanly. These boundaries are not embarrassments, they are signposts. Each one marks an opportunity for deeper understanding. Historically, such edges have been remarkably productive. Classical mechanics worked extremely well until it encountered speeds close to that of light, and scales close to that of atoms. Its breakdown did not invalidate it. It revealed the need for broader frameworks. The same pattern appears here. When physicists say that current theories break down at the Planck length, they are not declaring defeat. They are acknowledging that the language of smooth spacetime and sharply defined distances may no longer apply without modification. At this scale, concepts that are usually kept separate become entangled. Measurement affects geometry. Energy influences uncertainty. Cause and effect blur at the edges. The familiar divisions that keep equations manageable begin to dissolve. This is not chaos. It is overlap. The Planck length marks the point where gravity, quantum behaviour and spacetime geometry all insist on being included at once. Existing theories can handle any two of these remarkably well. Handling all three simultaneously remains an open challenge. This challenge is not due to negligence or oversight. it reflects the depth of the problem. Unlike previous theoretical revolutions, there is no direct experimental guidance here. The energies required to probe Planck-scale physics are far beyond current capabilities. As a result, theory must advance cautiously, guided by internal consistency rather than immediate verification. This is why humility plays such a central role at this frontier. Physicists do not claim to know what spacetime looks like at the Planck scale. They do not claim that space becomes grainy, foamy, discrete, or continuous. Different approaches suggest different possibilities, and none has yet been confirmed. What they do claim is more modest and more solid, that the Planck length represents a boundary of current understanding, a point where new ideas are required, even if their final form remains unknown. This perspective helps avoid a common misunderstanding. When people hear that physics breaks down, they sometimes imagine that reality itself becomes undefined, that anything might happen, that predictability vanishes. That is not the case. The breakdown occurs in description, not in existence. The universe does not stop behaving, it simply stops behaving in ways that current theories can describe cleanly. There is a quiet reassurance in this. Nature is not fragile. It does not rely on human equations to function. It continues according to its own rules, whether they are fully understood or not. Science, meanwhile, remains a process rather than a finished map. Each theory is a tool shaped by the questions it was built to answer. When those questions change, the tools must adapt. The Planck length signals such a change. It invites new ways of thinking about space, time, and measurement. This invitation is not rushed. There is no deadline. Physics is not in a race to resolve the Planck scale. It proceeds deliberately, refining ideas, testing consistency, and waiting for opportunities to connect theory with observation. In the meantime, the boundary itself is informative. Knowing where understanding ends is as important as knowing where it works. It prevents overconfidence. It sharpens questions. It clarifies what remains open. At the Planck scale, physics does not claim mastery. It claims awareness. That awareness is a strength. It reflects a discipline that has learned from its own history, that understands progress comes not from insisting on completeness, but from recognizing incompleteness honestly. The edge of known physics is not a wall, it is a horizon. Beyond it lies uncertainty, yes, but also possibility. The same kind of possibility that once lay beyond atoms, beyond galaxies, beyond the idea that space and time could bend at all. The Planck length stands at this horizon quietly, not as a dramatic endpoint, but as a reminder that knowledge grows outward from the known, guided by patience, curiosity, and respect for the complexity of the universe, and that even when the map runs out, the journey does not. When people first encounter the idea of a smallest meaningful length, a particular image often springs to mind. Space as a mosaic, reality as a screen. Tiny squares laid out side by side, each one representing the smallest possible unit. The universe, in this picture, becomes a kind of cosmic display, built from pixels too small to see. It is an appealing image, familiar, comfortable, easy to picture. But like many helpful images in physics, it is also misleading if taken too literally. The question of whether space is continuous or discrete has a long history. Long before quantum physics, mathematicians and philosophers argued over whether distance could be divided forever, or whether division must eventually stop. A continuous line can be split endlessly, always yielding smaller segments. A discrete line is built from steps, no matter how small. Everyday experience encourages the continuous view. A road does not appear to jump from point to point. A ruler does not skip gaps. Distance seems smooth, flowing, uninterrupted. Even when space curves, as gravity demands, it still feels like a single fabric rather than a collection of tiles. Physics reinforced this intuition for centuries. Classical mechanics treated space as infinitely divisible. Relativity refined this picture, allowing space to stretch and bend, but it remained smooth at every point. There was no smallest patch, no grain, no pixel. Quantum theory complicated this picture, but did not immediately replace it. Matter and energy became quantized, arriving in packets rather than flowing continuously. Space itself, however, was usually left untouched. It remained the stage on which quantum events unfolded. The Planck length brings this old question back into focus. If there is a smallest meaningful distance, does that mean space itself is made of discrete pieces? Does it come in units, like tiles on a floor? Are there literal pixels of space? The short answer is no one knows. And the longer answer is that the pixel image is a metaphor, not a claim. When physicists speak about discreteness at the Planck scale, they are rarely suggesting that space is literally built from tiny cubes arranged neatly in rows. That image borrows too heavily from human technology. Screens, grids, and pixels are solutions to engineering problems, not blueprints for reality. Instead, discreteness in physics usually means something more subtle. It refers to limits on what can be meaningfully distinguished, rather than limits on what exists. The Planck length marks a scale below which the usual idea of distance may no longer be well defined. That does not require space to be chopped into pieces. It only requires that attempts to define smaller separations stop producing clearer answers. This distinction is important. Imagine trying to mark positions on the surface of a lake during a gentle rain. From a distance, the surface looks smooth. Up close, ripples appear. The surface still exists everywhere, but pinpointing an exact location becomes less meaningful as motion increases. The difficulty lies not in the surface disappearing, but in precision losing relevance. Some approaches to quantum gravity suggest that spacetime has a kind of discreteness built into it. Others suggest it remains continuous, but noisy. Still others suggest that space is not fundamental at all, but emerges from deeper relationships. What they share is caution. The phrase pixels of space is often used as a teaching aid. It gives intuition a foothold. It helps communicate the idea that infinite precision may not be possible. But taken literally, it risks oversimplifying a profoundly subtle issue. In some theoretical frameworks, space behaves as if it has a smallest resolvable unit, without being composed of identical blocks. In others, distance emerges statistically, like temperature emerging from the motion of many particles. No single microscopic thermometer exists, yet temperature is real and measurable. In this view, space may be smooth in a deeper sense, while still resisting infinite subdivision in practice. It is also worth noting that discreteness and continuity are not always opposites in physics. Quantum fields, for example, are continuous entities that produce discrete outcomes. A field spreads smoothly across space, yet measurements reveal individual events. Light behaves this way. Matter behaves this way. Spacetime could behave similarly. Theories exploring these ideas do not agree on details, and they are careful not to overstate conclusions. Some propose networks of relationships. Some propose fluctuating geometries. Some propose entirely new mathematical objects that do not resemble space at all in the usual sense. None of these proposals has yet been confirmed experimentally. This uncertainty is not a weakness. It reflects the difficulty of the problem. The energies required to probe the Planck scale are so extreme that direct tests are currently out of reach. As a result, ideas must be judged by internal consistency and compatibility with known physics, rather than immediate observation. That is why physicists resist simple statements like space is made of pixels. Such statements feel decisive, but they overshoot the evidence. The safer claim is more modest. At extremely small scales, the distinction between continuous and discrete may lose its usual meaning. Space may not fit neatly into either category. This possibility challenges intuition, but it aligns with how physics has evolved before. Wave and particle once seemed mutually exclusive. Classical and quantum once seemed incompatible. In time, deeper frameworks showed that the categories themselves needed revision. The same may be true here. Using gentle imagery helps, but only if it remains flexible. Space as a fabric, space as a surface, space as a network. Each image captures something and misses something else. The pixel image captures the idea of limits. It misses the idea of emergence. What matters for understanding the Planck length is not whether space is made of pieces, but why asking for smaller pieces stops being meaningful. That reason lies in the interplay between measurement, energy, and gravity, not in a hidden grid. At scales far above the Planck length, space behaves beautifully as a smooth continuum. Geometry works, distance makes sense. The pixel question never arises. Only when questions push beyond that comfort zone does the metaphor appear, trying to give shape to something that resists direct description. There is no need to rush to an answer here. Physics is still listening, still exploring, still refining its language. For now, it is enough to say that space does not obviously come in pixels, but it may have limits that behave as if something like pixels exist. Not as building blocks, but as boundaries of resolution. That nuance matters. It preserves calm curiosity without forcing premature certainty. It allows multiple ideas to coexist while evidence accumulates. It respects the difference between metaphor and mechanism. And perhaps most importantly, it reminds us that nature is under no obligation to resemble our tools. Screens have pixels because engineers chose them. The universe may have limits for entirely different reasons. In the quiet space near the Planck length, familiar categories soften. Continuous and discrete blur together. Precision yields to pattern. Description gives way to suggestion. And in that gentle ambiguity, physics continues its patient work, resisting simple images, favouring careful questions, and allowing understanding to grow at its own pace. Observation often feels passive. Eyes open, instruments point, data arrives. The world presents itself and knowledge follows. This picture is comforting, and at large scales it is mostly accurate. Looking at the moon does not change its orbit. Measuring the length of a table does not alter the table. But physics learned long ago that observation is never truly hands-off. To observe is to interact. Light must scatter. Signals must be exchanged. Energy must flow from one place to another. Even the most delicate measurement requires some form of contact, however subtle. And that contact always leaves a trace. At familiar scales, the trace is negligible. A thermometer does not noticeably cool the room. A camera does not disturb a landscape. The costs of knowing are small enough to ignore. As attention shifts towards smaller and smaller systems, those costs begin to matter. In the microscopic world, observation becomes an active process. To learn where a particle is, something must interact with it. To learn how fast it is moving, something must exchange momentum. The act of gaining information reshapes the system being studied. This is not a limitation of cleverness, it is a feature of reality. Quantum physics formalized this idea by showing that certain properties cannot be known simultaneously with unlimited precision. This is not because nature is hiding information, but because the act of acquiring one kind of knowledge interferes with acquiring another. Observation is participation. Importantly, this does not make knowledge impossible, it makes it conditional. Measurements remain reliable, but they come with trade-offs. Certainty in one quantity brings uncertainty in another. Precision is balanced, not absolute. As long as gravity remains negligible, physics learns to live with these trade-offs. Probabilities replace exact values. Ensembles replace single outcomes. Reality remains describable, even if not perfectly pinned down. The Planck scale changes the stakes. At distances approaching 1.6 times 10 to the minus 35 meters, the energy required to observe becomes impossible to ignore. To probe such tiny regions, enormous energy must be concentrated into extremely small volumes. That energy does not remain a neutral messenger. It becomes part of the system. Energy curves space-time. It influences gravity. It alters the very distances it is meant to reveal. At this point, observation does more than disturb a particle. It disturbs space itself. The distinction between observer and observed begins to blur. The measuring device, the measurement process, and the structure of space-time become inseparable. Knowledge is no longer something extracted cleanly from a system. It is something negotiated with it. This leads to a profound shift in perspective. At everyday scales, knowledge feels free. At quantum scales, it feels conditional. At the Planck scale, it begins to feel costly in a physical sense. Gaining information requires altering the environment so significantly that the information itself becomes ambiguous. This is why physicists speak of limits to measurement rather than limits to existence. Reality does not disappear when observation becomes difficult. It simply refuses to present itself in the same way. The universe does not forbid questions. It changes the price of asking them. There's a quiet elegance in this arrangement. Nature does not allow infinite precision for free. Every refinement demands a payment, and at some point the payment exceeds the value of the answer. Not because the answer is meaningless, but because the method has reached its natural boundary. This idea can feel unsettling, especially in a scientific culture that prizes exactness. But it also carries reassurance. Knowledge having costs does not undermine understanding. It grounds it. It reminds physics that information is not abstract. It is physical. It must be carried by energy, constrained by time, and embedded in space-time. There is no detached vantage point outside the universe from which perfect measurements can be made. Observers are part of the system they observe. This insight reshapes how the Planck length is understood. It is not simply a number marking smallness. It is a signal that the relationship between observation and reality has changed, that the familiar idea of standing back and measuring no longer applies. Instead, knowledge becomes relational. What can be known depends on how it is asked, what is used to ask it, and how strongly the question presses on the system. This does not reduce physics to subjectivity. Measurements remain objective, repeatable, and reliable within their domain. Different observers agree on results. Predictions hold. The universe remains consistent. What changes is the scope of applicability. At the Planck scale, the act of observation becomes so intrusive that it reshapes the very framework being measured. Space bends. Time hesitates. Distances fluctuate. The map interferes with the territory. Rather than being a flaw, this reveals something important about the universe: that it is not infinitely fragile, that it resists being dissected beyond coherence, that its deepest layers are protected not by secrecy, but by structure. There is a gentle humour hidden here. Human curiosity is relentless. It always asks what lies beneath, and beneath that, and beneath that again. The universe responds patiently, answering clearly for a long time, and then, quietly, it changes the terms of the conversation. It does not say no, it says slow down. Observation remains central to physics. Without it, theories drift unmoored. But observation is not omnipotent. It operates within physical constraints, just like everything else. The Planck scale highlights this balance. It shows that knowing is an action, not a passive reception. An action with consequences. an action that must be accounted for. Seen this way, the limits imposed by the Planck length are not obstacles, they are safeguards. They ensure that descriptions remain meaningful, that concepts are not stretched beyond usefulness, that physics remains grounded in what can be consistently said. There is calm in accepting this. The universe is not withholding truth, it is shaping how truth can be approached. Knowledge is not denied, it is contextualized. At scales where observation remains gentle, precision thrives. At scales where observation becomes overwhelming, precision gives way to pattern, probability, and restraint. This does not diminish understanding, it deepens it. It invites physics to refine not only its tools, but its expectations, to recognize that some questions demand new forms of answer, that some limits protect coherence rather than threaten it. The role of observation, then, is not simply to reveal reality, but to participate in it responsibly, to listen as much as to probe, to recognize when asking harder no longer means asking better. The Planck scale, the universe asks for that maturity, and physics, carefully and patiently, is learning how to respond. Black holes are often introduced as cosmic extremes, objects so dense that light cannot escape, regions where gravity overwhelms everything else. They are sometimes described with drama, as if they sit outside the normal rules of the universe. But in physics, black holes are interesting for a quieter reason. They bring multiple limits together in one place. They are where gravity, space, time, and measurement all press against their boundaries at once. Far from a black hole, space behaves calmly. Time flows normally. Distances can be measured without complication. The laws of physics operate comfortably within familiar regimes. As one moves closer, that comfort slowly erodes. Gravity grows stronger. Time stretches. Space curves more steeply. Nothing sudden happens at first. The changes are gradual, predictable, and well described by existing theory. This smooth transition is important. It shows that black holes are not glitches in the universe. They are natural consequences of gravity operating under extreme conditions. One of the most discussed features of a black hole is the event horizon. This is not a surface in the usual sense. There is no wall, no shell, no material boundary. The event horizon is simply a location, a distance from the centre beyond which escape becomes impossible. From the outside, the event horizon behaves politely. An object crossing it does not trigger fireworks or cosmic alarms. No sudden flash marks the moment. Locally, nothing dramatic occurs. The object continues on its path, unaware that return is no longer an option. This lack of drama is often surprising, but it matters. It shows that black holes do not announce their extremes loudly. They hide them quietly. It is deeper inside that theoretical challenges begin to appear. According to classical descriptions of gravity, matter falling inward continues collapsing until it reaches a point of infinite density. This point is known as a singularity. At the singularity, curvature becomes infinite. Volumes shrink to zero. The equations stop providing meaningful answers. It is tempting to imagine the singularity as a real place, a point where everything ends, but physics treats it differently. A singularity is not a prediction of what exists. It is a signal that the theory being used has exceeded its range of validity. It marks a breakdown in description, not a confirmed feature of reality. This distinction is crucial. General relativity, which describes gravity so well across vast scales, does not include quantum effects. It assumes space-time is smooth and continuous everywhere. When pushed to extremes, this assumption produces infinities. Those infinities are not expected to survive in a more complete theory. Black holes therefore act as signposts. They show where current understanding runs out. Near the centre of a black hole, Densities and curvatures approach regimes where the Planck scale becomes relevant. Distances shrink toward the Planck length. Energies rise. Quantum effects can no longer be ignored. Gravity dominates every interaction. This combination places black holes at the intersection of all the deepest questions in physics. They are not laboratories in the experimental sense. No instrument can be sent inside and return data. But they are theoretical laboratories, places where ideas must confront their own limits. The event horizon itself plays a subtle role here. It marks a boundary not of violence but of information. Signals from inside cannot reach the outside. This makes black holes ideal testing grounds for questions about what can be known, what can be measured, and how information behaves under extreme conditions. Importantly, none of this requires speculation about what lies beyond the horizon. Physics does not need to imagine exotic interiors to learn from black holes. The limits appear even before those regions are reached. As matter falls inward, it is compressed into smaller and smaller volumes. The closer it gets to the centre, the more extreme the conditions become. Eventually, classical descriptions predict singular behaviour. That prediction is a warning, not a destination. It tells physicists that combining gravity and quantum mechanics is not optional in these regimes. It must be done to proceed further. Black holes therefore sharpen the importance of the Planck length. They create situations where distances naturally approach that scale, not because anyone is trying to measure them, but because gravity enforces it. In this way, black holes make Planck scale questions unavoidable. They show that extreme smallness is not an abstract curiosity. It appears naturally in the universe shaped by gravity itself. At the same time, black holes teach restraint. Despite decades of study, physics does not claim to know what happens at the very centre of a black hole. There are many ideas, many mathematical proposals, and many thoughtful arguments. None has been confirmed. Some suggest that singularities are replaced by new structures. Some suggest spacetime undergoes radical change. Some suggest that the concept of a centre dissolves entirely. What unites these ideas is their provisional nature. Black holes demand humility. They demonstrate that even the most successful theories can encounter domains where they no longer apply cleanly. They remind physics that prediction without confirmation must remain tentative. This humility is not weakness, it is discipline. The calm approach matters especially when black holes are discussed publicly. Sensational language can suggest that physics has discovered portals, paradoxes, or ultimate answers. In reality, black holes have taught something subtler and more valuable. They have taught where understanding ends and why. They have shown that gravity, when left unchecked, pushes space and time into regimes where measurement loses clarity. That the Planck scale is not an artificial construct, but a natural boundary reached by the universe itself. They have also shown that limits can coexist with order. Outside the event horizon, physics remains precise. Orbits can be calculated, radiation can be predicted, time dilation can be measured. The presence of an extreme interior does not destabilize the surrounding universe. This balance is reassuring. It shows that extreme limits do not infect everything. They are localized, contained, respectful of scale. Black holes therefore offer a powerful lesson, not about destruction, but about structure, not about endings, but about transitions. They sit at the boundary between what is known and what is not yet understood. They invite exploration without promising resolution. In doing so, they echo the lesson of the Planck length itself, that the universe has scales where familiar descriptions must give way to deeper frameworks. That recognizing those scales is part of progress, not a sign of defeat. Black holes do not reveal the smallest scales directly. They point toward them, quietly, firmly, without spectacle. And by doing so, they remind physics of its most valuable habit: to proceed carefully, to distinguish between what is described and what is inferred, and to accept that some of the most important insights come not from answers, but from recognizing the edges of understanding. When thinking about the early universe, it helps to let go of familiar images. There were no stars, no planets, no empty space waiting to be filled. Distances were not merely small. They were compressed to an extent that challenges ordinary language. Everything that now stretches across billions of light years was once contained within regions where separation itself behaved very differently. At those earliest moments, the universe was not arranged into structures. It was not calm or chaotic in any everyday sense. It was simply dense, hot, and tightly packed. Space existed, but in a state where the idea of distance had not yet settled into its familiar form. As cosmologists trace the universe backward in time, expansion becomes contraction. Galaxies draw closer, clusters overlap. Eventually, even atomic distances disappear. Matter and energy merge into a near-uniform state. The farther back this process goes, the smaller the relevant scales become. This is where the Planck scale quietly enters cosmology. When distances approach the Planck length, the assumptions that normally support cosmological models begin to soften, not because the universe becomes unknowable, but because the descriptions being used reach the edges of their applicability. Early universe physics depends heavily on measurement. Temperatures are inferred from radiation. Expansion rates are deduced from redshifts. Densities are calculated using well-tested relationships. For much of cosmic history, these methods work extremely well. They allow precise predictions and consistent narratives. But when the universe was extremely young, those same methods begin to encounter limits. At the earliest moments, distances between regions of space were so small that quantum effects and gravity could not be separated. Energy densities were enormous. Spacetime itself was under extreme conditions. The same issues that arise when probing tiny distances in the laboratory also arise naturally in the early universe. This is why Planck-scale physics matters for cosmology. It marks the point where extrapolating backward using familiar equations becomes uncertain, not wrong, but incomplete. The equations continue to produce answers, but those answers depend on assumptions that may no longer hold. In particular, classical descriptions of spacetime treat it as smooth and continuous. Quantum physics introduces uncertainty and fluctuation. In the early universe, both must apply at once. The result is a regime where distances, times, and energies interact in ways that current theories cannot fully capture. It is tempting to fill this gap with vivid stories, to imagine explosive beginnings, dramatic transitions, or exotic states of matter. But careful physics resists that temptation, and instead of claiming to know what happened at the very beginning, cosmology marks the boundary clearly. There is a period where existing models describe the universe extremely well, and there is a period earlier than that where those models must be treated with caution. This caution is not a weakness, it is a strength. The early universe is not described as mysterious because it is unknowable, but because knowledge must be earned carefully. Each step backward in time relies on measurements made in the present. Observations of cosmic background radiation, measurements of elemental abundances, studies of large-scale structure. These measurements anchor cosmology to reality. They ensure continuity between what is observed now and what is inferred about the past. As long as the scales involved remain comfortably above the Planck length, this continuity holds. Predictions align with observation. Models remain robust. As the Planck scale approaches, continuity becomes less certain, but not broken. The early universe does not suddenly detach from measurement. Instead, measurement begins to rely more heavily on inference and less on direct description. Patterns matter more than precise values. Relationships matter more than exact distances. This is an important shift to appreciate. The Planck length does not appear in cosmology as a dramatic cut-off. It appears as a signpost, a reminder that the universe's earliest moments sit at the edge of current understanding. Below this scale, physics does not claim to have a clear picture. It does not claim to know whether spacetime was smooth, fluctuating, discrete, or something else entirely. Different ideas exist, but none are confirmed. What is confirmed is that extrapolating known laws indefinitely backward leads to conditions where those laws strain against their own assumptions. This is why physicists speak carefully about the beginning. They do not say the universe began at a singular point that can be described fully. They say that descriptions break down at very early times, that the language of space and time may need revision to go further. In this sense, the Planck scale plays a similar role in cosmology as it does in measurement. It marks where questions must change, not where reality ends. This perspective keeps the listener grounded. There is no need to imagine the early universe as chaotic beyond comprehension. Nor is there a need to imagine it as neatly ordered in ways that current physics cannot justify. It was governed by laws, even if those laws are not yet fully known. Importantly, the uncertainty here does not undermine the rest of cosmology. The universe's later evolution remains extraordinarily well understood. Expansion rates, structure formation, and cosmic history are described with impressive accuracy across vast spans of time. The unknowns are confined to a narrow window near the very beginning. This narrowness is reassuring. It shows that limits at extreme scales do not destabilize the entire picture. They are localized, much like the Planck length itself. There is also a gentle continuity between cosmology and measurement that emerges from this view. The same principles that limit how precisely distances can be measured in a laboratory also limit how precisely the earliest moments of the universe can be described. In both cases, energy, gravity, and quantum effects conspire to soften precision. This parallel is not accidental. It reflects the unity of physics across scales. Whether examining a tiny region of space or tracing the universe back toward its origin, the same boundaries appear. The same caution applies. The same humility is required. There is something quietly elegant about this symmetry. The universe does not have separate rules for the very small and the very early. It has consistent principles that express themselves differently depending on context. The Planck scale is where those principles meet most intensely. Rather than offering dramatic answers, this meeting offers perspective. It reminds us that the story of the universe is not fully written in sharp numbers. It is written in patterns, relationships, and gradual transitions from the uncertain to the familiar. The earliest universe remains an open chapter, but not a blank one. Observations continue to refine models. New ideas continue to be tested against what is already known. Progress is slow, deliberate, and grounded. In the meantime, the Planck length stands quietly at the boundary, not as a barrier, but as a guide. It tells cosmology how far current tools can go with confidence. It encourages care beyond that point. And it ensures that speculation remains tethered to measurement, even when direct description becomes difficult. The universe began in conditions far removed from everyday experience, but it did not begin in a way that defies understanding entirely. It began within a framework that still respects limits, continuity, and structure. And in recognizing those limits, cosmology remains one of the most grounded sciences of all. When physics reaches a boundary where familiar tools no longer apply cleanly, it does not arrive at a single answer. It arrives at a conversation. Multiple ideas emerge, each trying to illuminate the same darkened region from a different angle. This is not confusion. It is how frontier science behaves. The question of the smallest meaningful scale has invited exactly this kind of response. All approaches begin with the same motivation: Gravity and quantum physics both work extraordinarily well in their own domains, but they resist being combined. Near the Planck length, that resistance can no longer be ignored. Any theory that hopes to describe this regime must account for both at once. From there, paths diverge. Some approaches begin by rethinking spacetime itself. Instead of treating space and time as fundamental, they explore the idea that spacetime may emerge from deeper relationships. In these views, distance is not a basic ingredient of reality, but a large-scale effect, similar to how temperature emerges from the motion of many particles. At very small scales, the familiar notion of distance may simply not exist in the way it does elsewhere. Other approaches keep spacetime closer to center stage, but modify its structure. They explore whether geometry itself might become quantized, acquiring a smallest meaningful unit without turning into a literal grid. In these pictures, space is not made of blocks, but it may resist infinite subdivision in subtle ways. Still others focus on symmetry and consistency. They ask which mathematical structures can accommodate both quantum uncertainty and gravity without contradiction. Rather than offering concrete images of space-time, they aim to ensure that the rules governing it remain self-consistent under extreme conditions. Each of these approaches has strengths. Each has open questions. None has yet been confirmed by experiment. This diversity can sometimes be misunderstood as disagreement or rivalry. But within physics, it is recognized as something healthier. It reflects the difficulty of the problem, not a lack of direction. When evidence is scarce, exploration broadens. Disagreement at the frontier is not a sign that scientists cannot agree on basics. It is a sign that they agree on the basics strongly enough to explore their consequences honestly. All approaches accept the same well-tested principles at accessible scales. All accept that any successful theory must reproduce known physics where it has been confirmed. The differences lie in how to extend that success into uncharted territory. Importantly, these approaches are not mutually hostile. Ideas cross-pollinate. Techniques developed in one framework often find use in another. Insights gained in one context inform questions elsewhere. Progress is rarely linear and rarely confined to a single path. There is also a shared humility underlying these efforts. Physicists working on the smaller scales are careful with language. They speak of proposals, frameworks, and models, not final answers. They distinguish between mathematical consistency and physical reality. They recognize that elegance alone is not enough. This caution is not pessimism, it is discipline. History offers many examples of competing ideas eventually converging. Atoms were once disputed. Waves and particles were once seen as opposites. Space and time were once thought independent. In each case, disagreement preceded clarity. The search for understanding at the Planck scale follows the same pattern. Another important point is that these theories are not built in isolation from observation. Even without direct experiments at extreme energies, they're constrained by what is already known. Any viable proposal must align with established results in particle physics, cosmology, and gravitational measurements. This shared constraint keeps speculation grounded. It also keeps the conversation calm. Rather than racing toward dramatic claims, the field advances through careful comparison. Which ideas reproduce known behaviour? Which avoid internal contradictions? Which offer testable consequences, even if those tests lie far in the future? There is a quiet patience here. Physics does not demand immediate resolution. It allows ideas to mature, interact, and sometimes fade when they no longer prove useful. Disagreement is not a problem to be solved quickly. It is a phase to be navigated thoughtfully. The Planck length sits at the centre of this discussion, not as an answer, but as a reference point. All approaches must account for why measurement appears to lose clarity at this scale. All must explain why gravity and quantum effects collide here rather than elsewhere. In that sense, the shared goal is clear. The aim is not to declare what spacetime is made of. It is to understand how space, time and measurement behave when pushed to their limits. It is to find a framework that respects both the success of existing theories and the boundaries they encounter. This shared aim matters more than the differences in method. From the outside, it can be tempting to frame these ideas as competing camps. From the inside, the picture is more cooperative. Researchers attend the same conferences, read the same papers, and critique one another's work constructively. Progress comes from dialogue, not dominance. There's also an appreciation that the final picture may not resemble any current proposal exactly. History suggests that the eventual framework often borrows elements from multiple ideas, while discarding others entirely. This expectation keeps confidence in check. Rather than asking which theory will win, physics asks which questions are most productive, which assumptions deserve scrutiny, which concepts may need revision. At the smallest scales, even the idea of scale itself may be part of what needs rethinking. This openness is a strength. It allows physics to adapt rather than ossify. It ensures that curiosity remains active without becoming reckless. For listeners, there is reassurance here. The lack of a single answer does not mean the field is lost. It means it is alive. The Planck length marks a region where certainty softens, but purpose remains. Multiple paths are being explored, guided by shared principles and mutual respect. In time, evidence will narrow the possibilities. New observations may rule out some ideas and support others, or they may suggest an entirely new direction. Until then, the conversation continues at a measured pace. Disagreement remains calm, speculation remains disciplined, and the shared goal remains clear: to understand the deeper structure of reality without forcing it into premature conclusions. That patience is not hesitation. It is how understanding grows when the questions are genuinely difficult. And at the smallest meaningful scale, difficulty is not a flaw. It is an invitation to think carefully, together. As ideas travel, they tend to simplify. Subtle concepts are compressed into neat phrases. Careful distinctions soften into slogans. This is almost unavoidable and usually harmless. But with something as delicate as the Planck length, a few common shortcuts can quietly distort what it actually represents. So it is worth slowing down and clearing the ground. The Planck length is not the smallest thing in the universe. It is not a particle. It is not a bead of space. It is not a tiny object waiting to be discovered. This is one of the most persistent misconceptions, and also one of the easiest to correct. The Planck length does not describe something that exists in the way atoms exist, or even in the way fields exist. It does not sit somewhere, and it cannot be pointed to. What it describes is a limit on measurement. More precisely, it marks a scale at which the usual concept of distance stops behaving in a reliable way. It tells physics that asking for smaller and smaller separations using familiar tools may no longer sharpen understanding. That is very different from saying that reality itself stops. Another common misunderstanding follows closely behind the first. The idea that below the Planck length, nothing exists at all. That space simply ends, like a road cut off at a cliff. This is not what current physics suggests. There is no evidence that reality abruptly disappears at this scale. There is no indication of a hard boundary where existence switches off. What disappears is not space, but clarity. The clarity provided by current descriptions. It's helpful to think of the Planck length as a statement about language, not about being. Physics describes reality using concepts like distance, time, energy, and position. These concepts work extraordinarily well across an enormous range of scales. The Planck length marks the point where those concepts may need revision, not where the universe runs out of content. In that sense, the Planck length is not a wall, it is a warning label. It says that beyond this point the familiar instructions may no longer apply. Another oversimplification is the idea that the Planck length represents a smallest unit of space, like a pixel in an image. This metaphor can be useful at first, but it quickly breaks down. Pixels are identical, they're arranged neatly, they tile a surface cleanly. The Planck length does not imply anything like this structure. It does not suggest that space is built from identical blocks or laid out on a grid. If space-time has structure at very small scales, it is almost certainly subtler than that. Current theories do not agree on whether space is discrete, continuous, emergent, fluctuating, or something else entirely. The Planck length alone does not settle this question. It simply tells us where our existing descriptions lose precision. There's also a tendency to treat the Planck length as a prediction, as if physics has confidently announced that this is where something dramatic happens. That too is misleading. The Planck length is not a prediction of an event or a phenomenon. It is a scale derived from combining well-established principles. It emerges mathematically when gravity, quantum behaviour, and space-time structure are all taken seriously at once. In that sense, it is a consistency requirement, not a forecast. It does not say what happens at that scale. It says that something different must be happening, because existing frameworks cannot all apply simultaneously without tension. Another gentle correction concerns certainty. It is sometimes implied that physics knows exactly what fails at the Planck length, that equations explode, that infinities appear, that everything becomes meaningless. The reality is calmer. Some calculations do produce infinities, but physicists recognize these as signs that the equations are being pushed beyond their valid range. They are treated as indicators of incompleteness, not as literal features of reality. This distinction is important. Infinities in physics are rarely accepted as physical truths. They are usually signals that a deeper description is required. The Planck length sits right at such a signal. It tells physics where to be cautious, not where to stop thinking. It is also worth correcting the idea that the Planck length is something that could be directly measured with better technology, that if instruments were improved enough, this scale would eventually be probed directly. Current understanding suggests otherwise. The limitation here is not engineering, it is physical. Measuring distances this small would require energy so extreme that gravity would dominate the process, distorting space-time itself. The measurement would interfere with its own objective. This is why the Planck length is often described as a fundamental limit rather than a practical one. Not because nature is hiding something, but because measurement itself becomes self-defeating. Another misconception presents the Planck length as a final answer, as if identifying this scale somehow completes physics. In reality, it does the opposite. It opens questions rather than closing them. It highlights where existing theories meet their limits. It motivates new ideas. It encourages careful rethinking of basic assumptions. The Planck length is not conclusion. It is a prompt. It says, this is where things get interesting. There is also no requirement that the universe must behave dramatically below this scale. The word limit often triggers images of breakdown, chaos, or collapse. But limits in physics are often gentle. The speed of light is a limit, yet nothing dramatic happens as objects approach it locally. Absolute zero is a limit, yet temperatures can approach it smoothly. The Planck length may behave in a similar way. Reality does not slam into it. Descriptions gradually lose sharpness. This gradual softening is important to keep in mind. It prevents unnecessary anxiety about what lies beyond. Physics is not standing on the edge of an abyss. It is standing at the edge of its current vocabulary. And vocabulary can change. Perhaps the most reassuring correction of all is this. The Planck length does not diminish reality, it enriches it. By showing that measurement has limits, it suggests that the universe is not exhaustively captured by any single framework, that there may be aspects of structure and behaviour that require new ways of thinking, and this is not a threat to understanding, it is an invitation to deepen it. The Planck length is not the smallest thing, it is not the end of space, it is not a pixel, it is not a barrier, it is a reminder that physics is a dialogue between nature and description, that concepts earn their usefulness within certain ranges, and that knowing where those ranges end is part of knowing well. Seen this way, the Planck length becomes something gentle rather than intimidating, a marker of humility rather than finality. It tells us that reality is not obliged to conform endlessly to human expectations, and that when those expectations begin to fail, the appropriate response is not panic, but patience. Because every time physics has encountered such a limit before, understanding has eventually grown richer on the other side. Limits are often spoken about as if they are disappointments, a sign that progress has stalled, a reminder of what cannot be done. In everyday language, a limit sounds like a door closing, or a road ending abruptly. In science, limits tend to mean something very different. A limit is usually not a failure of understanding, but a refinement of it. It tells researchers where a description works well and where it needs to change. It draws a boundary not to restrict curiosity, but to focus it. The Planck length is one such boundary. Rather than acting as a prohibition, it acts as a signal. It says that the familiar language of distance, measurement, and precision has been pushed as far as it can go without revision. Beyond that point, asking the same questions in the same way stops being productive. This is not a dead end, it is a transition. Throughout the history of science, limits have played this role repeatedly. They have guided thinking by showing where assumptions break down and when new ideas are required. Consider the speed of sound. For centuries it was treated as just another measurable quantity. But when objects began approaching that speed, classical descriptions faltered. New ideas emerged, not to remove the limit, but to understand what it signified. The speed of light played a similar role. It was once thought of as just a very large number. Over time, it became clear that it marked a deeper structure of space-time itself. The limit did not constrain physics, it reshaped it. Temperature offers another example. Absolute zero is a limit that can never be reached. Yet this has not stalled the study of thermodynamics. On the contrary, it has deepened it. Understanding why absolute zero cannot be attained revealed fundamental insights into energy, entropy, and the behaviour of matter. In each case, the limit was not a flaw in theory. It was a feature that pointed toward a richer framework. The Planck length fits comfortably into this tradition. It identifies where current theories meet their limits of applicability. It shows where gravity, quantum behaviour, and measurement collide in ways that familiar descriptions cannot fully resolve. It does not tell physics to stop. It tells it where to think differently. This distinction is essential for maintaining trust in gradual understanding. Science does not advance by eliminating all uncertainty at once. It advances by reducing uncertainty where possible, and by clearly marking where uncertainty remains. Limits are the markers that keep this process honest. Without limits, theories would overreach. They would claim authority beyond their evidence. Boundaries prevent that drift. In this sense, limits protect science from itself. They ensure that explanations remain grounded, that claims remain proportional to evidence, that speculation remains disciplined rather than reckless. The Planck length protects physics in exactly this way. It prevents the language of smooth space-time and sharp measurement from being stretched into regimes where it no longer makes sense. Rather than weakening physics, this strengthens it. There is also something quietly optimistic about recognizing limits. It implies that knowledge is structured, that understanding grows in layers, that new questions emerge naturally when old ones are answered. The existence of a limit today does not mean a permanent barrier tomorrow. It means that progress will likely involve conceptual shifts rather than incremental refinements. History supports this view. When classical mechanics encountered limits, it did not vanish. It became a special case within a broader theory. When quantum mechanics challenged classical intuition, it did not discard previous results. It reframed them. The same pattern is likely here. The Planck length suggests that future theories may not simply extend existing ones downward. They may reorganize how space, time, and measurement are understood altogether. That is not a loss of knowledge. It is a reorganization of it. Limits also encourage creativity. When straightforward paths are blocked, new routes are explored, new metaphors are tested, new mathematical tools are developed. Boundaries force innovation not by restricting imagination, but by focusing it. In biology, limits on growth lead to complex regulatory systems. In chemistry, limits on bonding lead to rich molecular diversity. In geology, limits on pressure and temperature shape the structure of planets. In physics, limits on measurement shape the search for deeper principles. There is also a human dimension to this. Accepting limits requires patience. It requires comfort with partial understanding. It requires resisting the urge to declare final answers prematurely. These qualities are not always celebrated, but they are essential for lasting progress. The Planck length invites this patience. It reminds us that the universe does not yield its structure all at once, that understanding unfolds gradually, guided by evidence and constrained by consistency. There is no need to rush past this boundary. It will not dissolve under pressure. It will reveal more when the right questions are asked in the right way. Trust in gradual understanding does not mean complacency. It means confidence in process. Confidence that careful reasoning, honest uncertainty, and collaborative effort will continue to deepen insight over time. The Planck length does not signal an endpoint for physics. It signals a moment of reflection. It asks researchers to pause, reassess assumptions, and look for frameworks that naturally accommodate what has already been learned. Seen this way, limits are not disappointments, they are achievements. They mark the edges of reliable knowledge. They show how far understanding has reached, and they point clearly to where the next questions lie. Quiet optimism fits naturally here. The universe has been remarkably consistent in revealing its structure layer by layer. There is no reason to believe that progress has suddenly stopped. The presence of a limit simply indicates that the next layer will look different from the last. Different questions, different tools, different language, but still part of the same ongoing effort to understand reality as it is, rather than as it is most convenient to describe. Limits, in this light, are not failures to be overcome. They are features to be learned from, and in learning from them, physics continues its slow, steady progress, guided not by impatience, but by respect for the complexity of the universe. The Planck length sits at a scale so far removed from everyday experience that even comparison struggles to help. Human senses evolved to navigate meters, seconds, and kilograms. Hands grasp objects. Eyes judge distance. Ears measure time in rhythms and pauses. These instincts work beautifully within a narrow band of reality. The smallest meaningful length in physics lies far outside that band. At 1.6 times 10 to the minus 35 meters, the Planck length is not merely small. It is separated from human scale by an almost unfathomable gap. Between the width of a human hair and the size of an atom lies an enormous descent. Between an atom and the Planck length lies a far greater one. This distance from experience matters because intuition weakens as scale departs from familiarity. Concepts that feel obvious at one level become unreliable at another. Smooth surfaces become collections of molecules. Solid objects become mostly empty space. Time, which feels uniform, stretches and compresses under motion and gravity. The Planck length continues this pattern. It reminds us that intuition is a local tool, useful where it evolved, unreliable where it did not. There is humility in recognizing this. Physics has repeatedly shown that the universe does not owe humans intuitive explanations. The Earth is not flat. Time is not absolute. Matter is not solid in the way it appears. Each of these lessons required letting go of comfortable assumptions. The Planck length asks for a similar release. It suggests that distance itself may not behave the way intuition expects when pushed far beyond human scale. This is not a failure of understanding, it is an expansion of it. There is also a quiet symmetry worth noticing. The same species that struggles to imagine the smallest meaningful length also struggles to imagine the larger scales of the universe. Billions of galaxies, expanding space, distances measured in light years. The mind strains at both ends. Extreme smallness and extreme largeness meet in their resistance to intuition. In both cases, physics provides guidance where imagination falters. Equations, measurements, and observations replace mental pictures. Understanding becomes less about visualizing and more about trusting carefully built frameworks. This trust is not blind. It is earned through consistency and prediction. Yet even here, humility remains essential. Models are not reality itself. They are structured ways of describing it. They succeed where they apply, and they soften where they do not. The Planck length marks one such softening. It does not tell humans how to picture space. It tells them where picturing may no longer be the right approach. There is something quietly grounding about this. It places human understanding in context. We're neither at the center of the universe nor excluded from it. We are participants, equipped with tools that work remarkably well within certain ranges. Beyond those ranges, care is required. Connecting the smallest and larger scales also reveals a deeper continuity. The same physical laws that govern galaxies also shape the behavior of space at its deepest levels. Gravity curves space-time on cosmic scales and complicates measurement on microscopic ones. Quantum principles influence atoms and hint at uncertainty in geometry itself. There is no sharp divide between the very large and the very small. They are connected through shared structure. This connection encourages perspective. Human history often oscillates between overconfidence and self-doubt. At times, discoveries inspire the belief that understanding is nearly complete. At other times, unknowns loom so large that knowledge feels fragile. The Planck length sits between these extremes. It neither promises total understanding nor threatens collapse. It quietly indicates that knowledge has shape, that it expands outward from what is known, guided by limits that inform rather than obstruct. From a human point of view, this is reassuring. It suggests that confusion at extreme scales is not a personal failure, nor a scientific one. It is a natural consequence of asking questions far beyond the environment that shaped human perception. Even the tools used to explore these scales reflect this distance. Particle accelerators span kilometers. Space telescopes orbit far above the atmosphere. Mathematical structures replace sensory imagery. Understanding becomes collaborative and abstract. This is not a loss of connection. It is a different kind of connection. Humans may never directly experience the Planck length, just as they will never directly experience the birth of the universe or the interior of a black hole. But indirect understanding is still understanding. Patterns can be recognized, limits can be mapped, relationships can be trusted. There's also a gentle lesson here about expectations. Not every meaningful question leads to a vivid answer. Some lead to boundaries, some lead to refined uncertainty, some lead to the recognition that a concept works well in one context and not in another. These outcomes are not lesser forms of knowledge, they're essential ones. Avoiding grand conclusions helps keep this perspective balanced. The Planck length does not demand a final interpretation of reality. It does not require philosophical closure. It simply invites reflection on scale, description, and humility. It reminds us that the universe is vast not only in space but in depth. That understanding has layers. That progress is often quiet. Human perspective matters here, not because it defines reality, but because it shapes how reality is approached. By recognizing the distance between experience and extreme scale, physics avoids overreach. It stays honest about what is known, what is inferred, and what remains open. This honesty is one of its strengths. The Planck length does not diminish the human role in understanding the universe. It situates it. It shows that curiosity can extend far beyond experience, while still respecting the limits of description. In that balance lies something deeply human, a willingness to ask, a patience to listen, and an acceptance that some answers arrive not as pictures, but as principles. At the smallest scales, as at the largest, understanding does not come from forcing clarity. It comes from allowing complexity to exist without rushing to simplify it. That acceptance is not resignation, it is maturity. And within it, human understanding continues to grow, quietly and steadily, guided by curiosity, bounded by humility, and connected across scales that stretch from the vastness of the cosmos to the smallest meaningful measure of space. At this point, it is natural to wonder why any of this still matters. If the Planck length sits so far beyond direct experience, and if current physics cannot yet describe what happens there in detail, why does it continue to hold attention? Why do physicists return to it again and again, carefully circling the same boundary? The answer is quieter than it might seem. Physics is not driven only by what can be built or applied. It is driven by coherence, by the desire for descriptions that fit together without contradiction. The Planck length matters because it marks a place where that coherence is under strain. Modern physics is remarkably successful. Quantum mechanics predicts experimental results with extraordinary accuracy. Relativity describes gravity and spacetime with equal confidence. Each theory has been tested again and again across decades and across continents. Their success is not in doubt, and yet they do not quite agree with each other. This disagreement is not visible in everyday situations. It only appears when questions are pushed to extremes. Extremely high energies, extremely small distances, extremely early moments in cosmic history. In these regimes, the Planck length appears not as an abstract curiosity, but as a shared point of tension. Physicists care about this because unresolved tension signals incomplete understanding. The goal is not to reach the smallest possible scale for its own sake. The goal is to understand how the pieces of physics fit together as a whole. A theory that works only in isolation, no matter how accurate, is not the final word. It is a chapter. The Planck length marks where chapters meet. There are also practical reasons, though they are long-term rather than immediate. History shows that deep theoretical questions often lead to unexpected consequences, not because applications are planned in advance, but because understanding reality more clearly changes what becomes possible later. Quantum mechanics itself offers a clear example. It began as an attempt to explain puzzling experimental results about light and atoms. No one studying those questions imagined computers built on quantum principles or medical imaging techniques derived from nuclear physics. Those developments came later, built on foundations laid by curiosity rather than utility. The same pattern may hold here. Understanding the limits of measurement helps physics avoid false assumptions. It prevents the extension of models into regimes where they no longer apply. This protects not only fundamental theory, but everything built on top of it. In practical terms, this means ensuring that predictions remain reliable, that calculations do not silently rely on assumptions that break down under extreme conditions, that cosmological models, particle theories, and gravitational descriptions remain internally consistent. The Planck length acts as a safeguard in this process. It reminds physicists where caution is required, where extrapolation must be treated carefully, where confidence should soften into inquiry. There is also a methodological reason this matters. Physics advances by knowing not only what it can explain, but what it cannot yet explain. Clear boundaries sharpen research. They focus effort. They guide questions toward productive directions. Without such boundaries, inquiry becomes diffuse. The Planck length provides a clear marker. It tells researchers where existing tools reach their limit. It suggests where new concepts may be needed. It helps structure the search rather than leaving it open-ended. Curiosity plays a central role here. At its core, physics is driven by a simple impulse: to understand how the universe works, not how to control it, not how to exploit it, but how to describe it honestly. The Planck length challenges physicists to confront the deepest assumptions behind that description. What does it mean to measure something? What does it mean to define distance? What does it mean to speak about space at all? These are not idle questions. They sit at the foundation of every physical theory. By revisiting them, physics renews itself. There is also value in recognizing what the Planck length does not promise. It does not guarantee a dramatic breakthrough tomorrow. It does not suggest that a single, elegant equation lies just out of reach. It does not offer a shortcut to ultimate understanding. What it offers instead is patience. It encourages physics to move slowly where evidence is thin, to resist oversimplification, to accept that some questions take generations to mature. This attitude is easy to overlook, but it is one of the discipline's strengths. Science has advanced not by rushing to closure, but by allowing uncertainty to persist where it must. The Planck length legitimizes that uncertainty. It says that not knowing is not a failure, provided the boundary of not knowing is clearly marked, provided claims remain proportional to evidence, provided curiosity remains active. This perspective also matters beyond physics. It models a way of thinking that values depth over speed, understanding over answers, process over outcome. In a world that often rewards immediacy, this slower rhythm offers balance. Even for those who never study equations or experiments, there is something grounding in the idea that the universe has layers of understanding, each approached in its own time. The Planck length sits in one of those deeper layers. It is not a place where physics stops caring. It is a place where care increases. There is a subtle continuity running through all of this. From laboratory measurements to cosmic observations, from everyday distances to the smallest meaningful scale, the same commitment to consistency applies, the same demand that descriptions make sense together. This continuity is what keeps physics unified. Without it, theories would fragment, results would become isolated, understanding would splinter. The Planck length helps prevent that by highlighting where unity is incomplete. As this chapter draws toward a quieter close, it is worth returning to the simplest reason this still matters. Humans ask questions because they want to understand their place in the universe, not just where they are, but how reality itself is structured. The Planck length speaks directly to that impulse. It touches on the nature of space, measurement, and knowledge itself. It does not provide a final answer. It provides orientation. It tells us how far current understanding reaches and where it begins to thin. It invites curiosity without demanding resolution. It keeps inquiry alive without pushing it into speculation. That balance is rare and valuable. The Planck length matters not because it is small, but because it is honest. Honest about what is known, honest about what is not, honest about the work still to be done. and in that honesty, physics continues its slow, careful progress, guided not by urgency but by curiosity, not by promises of application, but by the desire to understand, quietly, patiently, and with respect for the depth of the universe it is trying to describe. Standing at the smallest edge does not feel like arriving somewhere. It feels more like pausing, like reaching the point where familiar paths narrow, not because the landscape ends, but because it changes character. Throughout this journey, measurement has been the quiet guide. Distances compared, times counted, energies inferred. Measurement is how physics speaks to the universe, and how the universe replies in return. It is a conversation that has worked remarkably well for centuries. This moment is not unique in science. It appears whenever understanding approaches the edge of its current language. Early astronomers didn't know what stars were made of. That uncertainty did not stop observation. It guided it. Chemists once did not know the internal structure of atoms. That did not halt chemistry. It deepened it. Each time, not knowing was not an obstacle but a condition of progress. The Planck length sits in that same tradition. It reminds physics that measurement is not a mirror held up to reality. It is an interaction with it. A structured way of asking questions that works beautifully within certain ranges and less cleanly beyond them. There is calm in recognizing this. The universe does not demand that everything be measurable in the same way. It does not insist that every scale yield to the same tools. It allows clarity where clarity is possible and invites patience where it is not. Not knowing in this sense is not ignorance, it is awareness. Science advances by distinguishing between what is known, what is inferred, and what remains open. The Planck length helps draw that distinction with honesty. It marks where confidence gives way to care. This care is visible in how physicists speak about the smaller scales. Claims are measured, language is cautious, conclusions are provisional. This is not hesitation, it is respect for the problem. At this edge, the goal is not to force answers into shape, but to let better questions emerge. There is also something deeply human about this posture. Curiosity does not always seek resolution. Sometimes it seeks orientation, to know where one stands, to know how far understanding reaches, to know where mystery begins. The Planck length provides that orientation. It does not tell us what lies beneath the smaller scale. It tells us how to approach that unknown responsibly, without exaggeration, without fear, without pretending that uncertainty is something to be embarrassed by. In everyday life, uncertainty often feels uncomfortable. Decisions demand clarity. Plans demand closure. But in science, uncertainty has a different role. It marks fertile ground. It signals that existing ideas have been pushed far enough to reveal their own outlines. There is quiet value in standing there. The smallest edge is not a cliff. It is a shoreline. The water beyond is not empty, but not yet charted. Maps end not because the ocean disappears, but because navigation requires new methods. Measurement, so reliable elsewhere, becomes less decisive here, but it does not lose relevance. It changes role. It becomes a guide to where description must evolve, rather than a tool for extracting finer detail. This shift can feel subtle, but it matters. It encourages physics to treat limits as information, to read them as messages rather than obstacles, to understand that some questions ask for patience rather than precision. There is no urgency here, no countdown to resolution. The universe is not withholding answers on a schedule. Understanding unfolds at its own pace, shaped by insight, evidence, and time. The Planck length is part of that unfolding. It sits quietly at the boundary of current knowledge, not demanding attention, but rewarding it. It invites reflection on what it means to know something at all, on how measurement, language, and reality interact. Standing here, it becomes clear that science is not a quest for final answers. It is a practice of careful listening, listening to what measurements allow, listening to where they resist, listening to the shape of uncertainty itself. This listening does not weaken confidence, it refines it. Confidence in science does not come from claiming completeness. It comes from knowing where completeness has not yet been earned, from being clear about what is provisional and what is established. The Planck length sharpens that clarity. It shows that reality is not obligated to fit neatly into human frameworks. That understanding is an ongoing negotiation between curiosity and constraint. There is peace in accepting this, rather than striving to resolve the smaller scale into something tidy and final. Physics allows it to remain open, a place of active inquiry rather than settled doctrine. This openness keeps the field alive. It also offers something to those listening. A reminder that not every meaningful journey ends with a conclusion. Some end with a deeper appreciation of where one stands. The smallest edge is one such place. Here, certainty softens, curiosity remains, and understanding continues, not as a destination, but as a process. The universe does not ask to be fully known all at once. It asks to be approached with care. Standing at this edge, measurement pauses, but meaning does not vanish. It simply waits, shaped by questions still forming and answers still to come. And for now, that is enough. The Planck length is often introduced as an extreme number, a distance so small that it resists imagination. But by now, it has become clear that its importance does not lie in how tiny it is. It lies in what it represents. The Planck length marks a boundary of meaning rather than a boundary of size. Physics does not discover a smallest object or a final layer of reality. Instead, it discovers a point where familiar ideas about measurement, distance, and precision stop fitting together cleanly. The tools that have worked so well across vast ranges begin to overlap in ways that demand care. This is not an ending, it is a transition. Throughout this journey, one theme has remained steady. Physical law does not fracture at extreme scales. It remains consistent, even when descriptions soften. Gravity continues to shape space-time. Quantum behaviour continues to govern uncertainty. Relativity continues to link space and time. The Planck length does not disrupt these principles. It reveals where they meet most intensely. That continuity matters. It reassures that the universe is not stitched together from incompatible pieces. The same laws that govern falling apples, orbiting planets, and expanding galaxies also guide the deepest limits of measurement. Nothing new appears out of nowhere. Nothing vanishes without reason. Instead, understanding evolves by recognizing where language must change. Mystery plays a quiet role in this process, not the kind of mystery that signals confusion or failure, but the kind that signals depth. The Planck length shows that reality is not exhausted by what can currently be measured, that there may be aspects of structure and behaviour that require new concepts to describe. This does not diminish reality, it enriches it. A universe that can be fully captured by a single framework would be a simpler place. The universe revealed through physics is not simple in that way. It is layered, subtle, patient. It offers clarity where clarity is possible, and invites restraint where it is not. The presence of mystery does not weaken trust in physical law. On the contrary, it strengthens it. It shows that laws are not brittle. They do not shatter when pushed to extremes. They bend, overlap, and signal where refinement is needed. There is stability in that behaviour. The Planck length does not threaten the reliability of science. It confirms it. It demonstrates that physics is attentive to its own limits, careful about its claims, and willing to mark the edges of understanding honestly. This honesty is one of science's quiet strengths. For those listening, there is reassurance here. The universe is not suddenly unknowable because a boundary has been reached. Most of reality remains beautifully accessible. Distances can still be measured. Time can still be counted. Predictions can still be trusted. The limits appear only at extremes far removed from everyday experience, and even there, they do not signal chaos, they signal care. The Planck length reminds us that knowledge is not a race toward final answers. It is a gradual alignment between questions and reality. When questions become mismatched to the structure of nature, answers soften rather than break. That softening is not a loss, it is guidance. It encourages physics to listen more closely, to refine its language, to approach the deepest questions without urgency or exaggeration. There's also a human comfort in this perspective. Not everything meaningful must be fully resolved. Some things are meaningful precisely because they remain open, because they invite reflection rather than closure, because they remind us that understanding is a process, not a possession. The smallest meaningful length in the universe does not reduce the wonder of existence. It adds to it. It shows that even at the deepest levels, reality retains richness beyond immediate reach. Space does not end. Time does not stop. Meaning does not vanish. Only certainty gives way to curiosity, and curiosity handled gently is a stable thing. It does not demand answers on a schedule. It does not collapse under uncertainty. It moves forward patiently, guided by evidence and humility. The Planck length sits quietly within that patience, not as a warning, but as a reminder that the universe is coherent even when it is not fully known, that mystery and law coexist without conflict. Standing back from the details, a calm picture emerges. The universe is governed by stable principles across enormous ranges of scale. Where those principles meet their limits, they do not fail. They invite deeper understanding. That invitation remains open. There is no need to rush toward conclusions, no need to resolve every question. The universe is not diminished by what remains unknown. It is sustained by what continues to be discovered. And for now, it is enough to know this. There is a smallest meaningful measure of distance. There are limits to precision. There are boundaries of description. And within those boundaries, reality remains vast, consistent, and quietly profound. That steadiness is worth resting in.